Perfect. So I think we can go started. So thank you very much for attending this introduction to SYCL. So it is divided in two sessions more or less. So I will do first a theory, an introduction to SYCL, and after we'll have some hands-on. It will be on Theta GPU, so maybe we'll have some work sharing issue or this kind of thing. I already put, I think, on the Slack channel the instruction how to be able to compile and run on Theta GPU. So if you want to go ahead, or if you know already SYCL, or if you just want to grab a node before everybody else, you can do that. I try a new thing to make a little survey. So we may have some survey question. Let's see, to keep it interactive. Please don't feel free to ask any question. So you can ask on the chat, or you can just unmute yourself and ask me any question. If we got too many questions, or if the discussion are too long, we can continue after by email or by chat, or after the hour or something like that. So it's really meant to be an introduction and maybe more an exchange. So if you have any question, I will put a little of resources. As you will see, SYCL now got a lot of traction, so you can feel a lot of good talk, lot of good material for different hardware, for different companies. You have like a conference who are now specialized on SYCL, in SYCLCon and everything. So finding material are not really too hard. So what I want to do here is maybe give you some design idea, or maybe what happened under the hood, so you can have like a bigger understanding of all of this new concept. And you will see some of things are similar to what Christian showed before in Cocos, and some of things are a little different. So let's get started, and as usual, don't hesitate to interrupt me or to ask a question. And we have a few SYCL experts on the chat. So we have Abhishek, who helped me, and we also Nevin, who is part of the SYCL committee and the C++ committee. So if you have tricky C++ question, it will be for him, because I'm not a C++ guru. So as I say at the beginning here, it's maybe more for the introduction. So I will give you maybe the ecosystem of SYCL and DPC++, what kind of ecosystem you can have, like how to install it if you want to install it on your own system, and how you can use it on compilers and all this kind of thing, and the theory. So to build SYCL, so it's a question, maybe it's a good start. So SYCL, let's see, it's SYCL has the difference to maybe OpenMP and Cocos and Raja. It's purely C++, so it can be implemented at the libraries like Cocos does, so purely libraries, or it can also be implemented at the SYCL, at the compiler level. So what Intel does and what also CodePlay does is like they built on compiler for SYCL. So inside the compilers, they have a SYCL option. So this allows you to have a little more better error message, to be able to do more optimization. So we'll not build SYCL, we'll build applications who are using SYCL, because building SYCL, it's, I mean, you need to build LLVM, and it's not a joy. So maybe to recap before kind of an overview of the portability, I will not explain. I think Christian did a really good job why you should find a portability layer to target accelerator, because you have some proprietary or at least low-level stuff, for example, CUDA, HEAP, or OpenCL. They are really low-level, so, and sometimes they are proprietary. So if you go from there, it will be hard to move from one hardware to the other. You have OpenMP. If you are in Fortran, it is your only choice. If you are in C++, you have other choice, but it is pragma-based. Some people don't like really pragmas, because it makes interacting with C++ a little more tricky. Also, you have, like you say, like it show Cocos, Raja, or Oka, who are more like abstraction layer developer libraries. So they did a lot of great things. Cocos really pushed the C++ community in the correct direction, but they are maybe like, how can I say, they are academic project, right? They are developed it by scientists for scientists. They are used only, not only, but majority by the DOE and for application. And after now you have SYCL, where SYCL is an industry standard. So it's developed by the same people who, the consortium who develop OpenCL. And you have it's open source, so you can download the specification and all of the kind of things. And it is really backed by industry. So you have, if you go on the SYCL website, you will have a lot of different vendors implemented for FPGAs, CodePlay, for example, did port SYCL for car manufacturers. They want to use that. So it's really like a more industry approach, let's say. And maybe if you want to go higher on the abstraction layer, you have this parallel STL. So where, you know, inside C++, now you can have some parallel algorithm, and some implementation exists with different backend, and one exists with a SYCL backend. So, and here I will target more, I will talk about SYCL. So SYCL is the name of the language, like OpenMP, and DPC++ is the Intel implementation of SYCL. It means data parallel C++, not the best kind of name, I think, but it is just the implementation of SYCL from Intel. So they add some extension and something like that. I will talk a little bit more later. So maybe just a quick overview to SYCL. So SYCL is really for C++ programmers. So if you don't like C++, you will not like SYCL. You have, and it's pure C++, so you have nothing new in C++, no new constructs. So this is why it can be implemented as a libraries. So you have no pragma, no new attribute, no language reduction, pure C++. So a lot of template and a lot of lambdas. It did bring a lot of ID from battle-tested OpenCL. So OpenCL was used for a long time. It's a really nice little piece of API. And they reuse, they didn't reinvent the wheel, they reuse platform, device, workgroup, range. The big difference is like in Cocos, for example, it is really single source. So you put your kernel at the same time as in your language. So not like, for example, in CUDA, where you need to have a .cu file. It's more like OpenMP. And like I say, it is developed by the same consortium who do Spear, Vulkan, OpenGL, and everything. So it's a big consortium with a lot of players in it. And if you want to download the specifications, the last table is called SYCL 2020. And I think it's important to talk a little bit about where SYCL can run. And I think the answer is it can run everywhere. So here it's a tree you can find on the SYCL website, and you saw all the different implementation of SYCL. So some of them are compiler, like I say, for example, for Intel. So it is open source. You can go on the Intel GitHub and you will find the data parallel C++ compiler with based inside LLVM. So you can, and with this compiler, you can target any CPU. They will use a TBB under the hood. They will have an OpenCL backend and a level 0 backend to target their CPUs, their GPUs, and their FPGA. And you will also have a CUDA backend developed in collaboration with CodePlay, where you can target NVIDIA. And this is what we will use in the presentation later. You have also CodePlay, who is another company who did a lot of things in compiler development for SYCL. And they can target really strange things. So for example, cars and everything. And they also have an NVIDIA backend using OpenCL. You have also Z-Link, 2c. I just talked about 2c because it is the best name. I think it did a good job with the name. And after you have HipCycle if you want to run on hip hardware. And you have NeoCycle if people have access to Tsubasa, the Japanese computer, you can try that. And after it will target their CPU only. So it's pretty large, big names with university, but also industry. So if you go in SYCL Tech, you will find a lot of examples, a lot of really good talk by people who are far more a better teacher and speakers than me. So it's really big now, and the traction was gained really fast because, like you will see, it's really tasting like C++. So it was really appealing for C++ people. So maybe a little jargon because after it's confusing. So DPC++, like I say, is just the Intel implementation of SYCL. It is also the name of the compiler that if you install OneAPI, who is a new big Intel software infrastructure like the NVIDIA HPC toolkit, now for Intel is called OneAPI, you will have a compiler inside which is called DPC++. And it is just a thin layer around their regular Clang++ that they develop open source. And like I say, if you go on the open source and you download their SYCL compiler, it's just based on LLVM. So the name of the compiler is just Clang++. And this is what we need. So on the later, we'll just use Clang++ as a compiler. So it's a compiler, so it's not trivial to install if you want to install it from source, but I'm pretty sure some of you in the audience are expert of doing that, so you can do that. And the good thing, if you build it on source, you can mix directly. You have the OpenMP backend too, because it is in main trunk LLVM, so you can use OpenMP and SYCL in the same code using the same compiler. So this is neat. We can talk later about that if you want more about the interop between OpenMP and SYCL. Or if not, OneAPI with this new HPC toolkit from Intel, it is available via apt-get. So on Ubuntu, you can just go on sudo apt-get install OneAPI if you put the correct deb and RSAK, and it will work. You can go also on the OneAPI website and develop a binary. And my favorite piece is just ask your sysadmin. There are always nice people who are here to help, and they will install OneAPI for you. You may need to ask a few times, but at some point they got really pissed off and they install stuff for you. At least it's my experience. So the ecosystem, as you mentioned and Christian mentioned, and some of you ask, if you just have a programming language is not enough, right? You need a lot of things. You need a debugger. You need some math library. You need a lot of things to be able to work. You need some IDE support and everything. So I just want to go quickly around the DPC++ that Intel developed but are not restricted to Intel hardware. For example, the first one I think is useful is this DPCT. So it's CUDA to data parallel C++. And it's help you migrate from CUDA to DPC++. So we'll take your CUDA and translate it to DPC++. It is not a compiler. It is not a source-to-source compiler. It's more or less a tool to help you. So you may still need to change some of the code and everything. But it's really useful if you really want to port your application, because like I'm sure a lot of you know, it's really not the same strategy if you are building a code from scratch or if you try to build a code from CUDA, directly porting your code from CUDA. And this tool will really help you. You have one MKL, so you will see everything is called one now. And it is just the implementation of MKL who will be accelerated for GPUs. Okay, so they took their MKL examples, they ported to GPU using SYCL, and now you can use it. So it is not only from Intel, you can also use it from other hardware. So for example, in the repo, I have example of one MKL running on CUDA. And the API, they didn't change the API. They only changed one thing, is like you need to pass a queue at the beginning, or if you use USM, you have absolutely nothing to change. So it should be a drop-in replacement. You have also one DPL. So this one, I will curious to see if you plan to use it or not. I have no idea. Is from to replace parallel STL or boost compute or something like that, where if you are really a good really into C++, you say, I want to stick to C++, I will use all this kind of nice C++ thing. So you can use one DPL, who is C++ standard library ported to SYCL. I forgot to say that you have also vTune. They didn't rename into one vTune or one debugger. So it gives you a lot of introspection, because maybe the difference with Cocos is like in Intel, SYCL is implemented as a compiler. So the compiler knows more things. So the debugging experience maybe a little more, in theory, should be a little more easy, because the compiler can give you more information. Where like Christian exists, if you are a library, you have far less control. It's really hard to be integrated, where here they have full control over everything. So you can have some nice error message, meaning it is C++, so it will not be 20 page long, but maybe just 2 page long. So let's say still a better incrementation. Do you have any question? If not, I will try something in the chat, if you don't mind. I'll put it on the Slack. So it is a trivia question, survey. Let me see, it's worked. So it's just a question, do you plan to use the parallel STL? I'm just curious because, like, maybe we are in the process of Argonne will receive Aurora, so we need to prioritize some implementation and everything. And I was just curious to see if because it's a big audience, so it's always nice to ask your audience, do you plan or not to use parallel C++? Because if it is the case, we can maybe invest more time testing, benchmarking it. And if it is not the case, I will just trust, will not invest specially a lot of amount to benchmark this thing or to do more tutorial presentation. So I think if you click on the link, you should be able to vote. And I can share in theory the result with you in live. The technology, when it's working, it is amazing. Oh, but it is not working. Why I have to think? Okay, so no. So it looks like 1/3 of you doesn't care about parallel STL. This is good. That means you are the same kind of C++ programmer as me. A little C++, but not too much C++. So this is good. Thank you very much for your feedback. Oh, how does this work? Oh. So now more the theory about SYCL. So what is really below SYCL, and what is really the main concept that you should learn to be able to do a real SYCL expert. Maybe some people will have a horrible flashback from their CS background. It is a new UML diagram, but I think, and it is bring from OpenCL. Yeah, pictures is worth 1,000 words. So I will just give you a big overview here. It doesn't need to remember everything. And after I will go explain a little bit. I think the most important thing are this triptych of platform, device, context, and command queue. So it's a quadric, I don't know, 4 things. So this is the main thing that we'll need to understand. I will talk later. But this is really the main concept where, for example, in CUDA you have streams who are corresponding to queues, but we don't have this concept of context, or at least not in the, if you go to the CUDA driver, you have context of context, but if you program in CUDA, you don't have. Same in OpenMP. In OpenMP, you don't even have command queues and context. So SYCL, in some way, is maybe lower level than CUDA. It's funny to say it's this way, but it gives you maybe more control when really want to do some really optimization or all this kind of thing. So I like this aspect where they don't hide so much things over you. So here it is the first SYCL code you will ever saw. Maybe some of you are always an expert. And it is this platform device context queue. So a platform is a collection of devices in the sense of things you have on your node sharing the same backend. Like I show you in the previous picture, sorry. You have different kind of backend. You have, for example, an OpenCL backend, Intel TBB backend, a HIP backend. So they are bundling all these backend differently on different platforms. And then on those platforms, you have devices right? And you can bundle these devices together on a context. And the context will be something ready to do memory isolation. So it will be really important in the future that a context is bound to a memory. And after, with a context and a device, you can create a queue, and the queue will be used to dispatch work and to allocate memory. Okay, so in the little example here, it is a simple example of SYCL. We'll show after even more simple example, but let's start with this one, is this platform device context queue. So I create a platform that I'll call capital P, and I can say, I want a platform where I have GPUs. So you have this concept of selector, which is part of the standard. So you can say, oh, please give me a platform where I'm sure I have only one GPUs. If you are running somewhere where you don't have GPUs, it will crash or something like that. After, from this platform, like I say, on the top platform are corresponding of a lot of devices, you can say, please give me all the devices. And here you can specify too, please give me only the GPU devices. And this thing return a vector of the devices within the platform, right? Like, for example, I don't remember on Summit, on Theta GPU, how many GPUs you have per node, but you have more than one. So you have a vector of device. Here, to simplify, I will just take the first one. But if you are MPI, you can take the MPI rank ID or something like that. You can do whatever algorithm you want to do to choose your device. You can also ID it over a different strategy. We can talk it later. And now I need to create a context. So to create a context, I just pass a device. So now I have a context with associated to this device. And now to create a queue, I pass this context and this device. So I think it's important. I am really explicit. You can find other tutorials, and we'll see later that you can do that in one line. Everything I did here in one line, but it's nice for Hello World tutorial, but for real application, you can have major drawbacks. So this is why here I think it's important for you to understand all this kind of hierarchy of different level of abstraction, because it's really fundamental. You can have as many queues as you want. You can have as many contexts as you want. So it doesn't matter. Now the question is maybe how a queue map to an hardware resources. So a queue to already a command streamer or this kind of something. And this one is purely implementation dependent. We can discuss how it works on Intel or something like that. But here we are already at the software level. And after you can use any tracer or something like that, if you want to get deep down in detail how this is mapped to hardware. So like I said before, the difference between CUDA and heap, it's like contexts are really explicit. Contexts are really important. They're an important piece of understanding. They are used for memory allocation. So the big impact is, in particular, if a kernel was submitted in a queue, for example, Q1, he will be able to access memory that only have been allocated on the same context as the one used to create Q1. So I will show you some example to see if it is clear or not. So like I said before, this one is really the explicit way. So you do all this kind of thing. And because as all programmer, we are lazy, you can just create a queue too. And you just create a queue, and the implementation will choose any platform, any device. So you can tune the default queue, the device, and it will just give you a queue. And after, you can go also up the hierarchy chain. So from a device, from a queue, you can get the device. From the context, you can get from the queue, you can get the context. So you have API to go either way. So this is nice. Maybe another queue if you are not in CUDA or OpenMP too. Queue are by default out of order. right? They did that for performance. So you need to be careful. You cannot assume in CUDA they are in order by default. In SYCL, they are out of order. So it's not because you first unqueue A and after unqueue B that they will be A will be executed after B, before B. It can be executed in another order. And everything is asynchronous by default. I think it's exactly like Cocos, only memory allocation and free are synchronous, all the rest are asynchronous. And you can use event to synchronize. We have some example later if you want to use event. Do we have any question right now between all those concepts? Is the device, queue, context are clear? No question, I will assume yes. Perfect. So maybe now the more important thing, we know how to have a queue, and now the question is, what can we do with queue? I heard that some people, some strange people in HPC need to allocate memory. Not really sure why, but I think it's important. So I will talk a little bit about this unified share memory. Here I use unified share memory maybe in a strange term. It's more like explicit allocation, because we'll see one of the new innovative ideas of SYCL is Christian talked a lot about this accessor view buffer and everything, but this one is really a little harder when you port your code to refactor your code to use buffer and accessor, where here I would just want to show the naive, maybe easier to port your code. I will start with that. So memory allocation from accelerator are really, really deep subject. You have a lot of subtleties. I will be happy to talk with you between all the different kind of which memory can migrate, which memory cannot migrate, and all of these kind of things. But I'm not sure it is really useful to spend too much detail on it. So I will just put you some documentation. And if you are interested on this topic, please don't hesitate to read it and to reach to me if you have any question. So in high-level view, you have two things. You have the malloc device. If you do malloc device, this memory is only accessible on the device, right? I will show you some example, but it's pretty trivial. You allocate memory on this device. So that means you cannot read it from the host. It's really a pure device memory. Like in OpenMP, you got an experience in OpenMP before, OpenMP target device. OpenMP, memalloc device, I think. You have also memalloc shared. Memalloc shared are accessing on both the device and the host. So if I tell you that you are like, I should use just malloc shared everywhere, I don't see any traceback. It's kind of nice because you can access it on device and the host. As you know, I'm pretty sure everybody knows on the call, programming on GPUs, what is hard is not really to write your kernel and to get good performance of your kernel. It's really more about data movement, to be able to minimize the data movement, because the PCI bandwidth is super low compared to the memory bandwidth of your GPU. So the real difficulties on GPU are the data transfer. If you use malloc shared, you have no control over data transfer first. It will be happened when it happened. So it may be a bad thing because it's really when the memory will be accessed, it will be transferred via page fault, for example. And like Christian showing this benchmark page fault can be really, really expensive. So memory malloc shared, you are asking for, how can I say? It's really to be lucky if you use malloc shared everywhere. That means you rely a lot on really good hardware and really good prefetching or whatever, smartness inside the runtime to be able to do things. But it is very convenient. So I think my advice is maybe more to use malloc device, the maximum you can, and shared only when it makes sense, when you really want to share. For the API, it's super easy. Malloc device, if you follow what I said before, we say that contexts are ready for memory allocation. So malloc, all the malloc device and malloc share take a context and a specific device. You are allocating memory on one particular device for one particular context. And it's maybe not trivial the first time you see, but if you think a little bit, you have a bijection between one device and one context. So to create a queue is really a pair of context and device. So they did something nice. It's like you can just create a queue to create to do a malloc, and it will work. Example here. So I take this more explicit approach and implicit approach that we saw before, and I allocate memory here really the most explicit way, right? In Zen of Python, they say explicit is better than implicit. So here I'm super explicit. I malloc a device who is the size as the first argument on this device and on this particular context. Maybe a good thing is this malloc device, because it is C++, this is templated, so you can pass the type. So you don't need after, to cast it to a float and here to put it the size of float. So this is a pretty nice C++ capabilities. And if you're implicit, if you want to fit on one slide or to impress your coworker by the beauty of SYCL and the non-verbosity of SYCL, you can do that. You can just create a queue. You don't even need to pass a GPO selector. By default, they will choose one device to run. And after, you can just create a malloc device and then queues. And it will work exactly the same. Okay, now the second question. Let's see, in theory, in my in the quiz, I put a second question. Does this code have a problem? So now I will test your HPC HPC capabilities. So I have a code here. I just set a number. I create one queue. I malloc to this queue. I create a second queue. I malloc to the second queue. And after I create a mem copy, and a mem copy will take just the data from A and run it on B. And you just need to send the number of bytes. So the question on the vote is this code is correct? And what do you think? Does this thing will work? Does this thing will not work? So if you go directly on the pooling, you should be able to see the difference. So let me see. I don't put here. Up. Let's put it here. I put other. I don't know why. Oh, I vote. Oh, okay. Strange. I will thinking we can see the result. It was not the correct thing. So let me open the result tab. Other. Okay. So does anyone want to see what other mean? So if somebody say other, what is your thinking? If somebody who say other can speak and say, what do you think will happen? Because it looked like at least that some people agree, some people say change, different context. So from other, if anybody want to work on the chat. Oh, it looks like different context is winning now. Maybe it's not a fair to show you the result of other people, maybe impact your selection. So, and it is true. So the problem is like different context. It's because, and it is something I see a lot in real code, right? It is really the first major problems that people hit when they put SYCL in production code, and it led to horrible debugging and understanding of the bug. And indeed, it is that. It's because this queue here, we create implicitly a new context, as we saw before. And this guy here, we create implicitly another context. And like I show you, the memory is only valid with a particular context. So that means here, when you do q.memcopy, it will try to access, for example, I will use q1 to access memory was initialized on B, who live in another context. So it doesn't matter if they live on the same device, they live on a different context. So in some implementations, they will just say a cryptic error message. For example, in OpenCL, I think it's CL kernel invalid argument. On other hardware, you can have maybe garbage result, 0 result. On some hardware, it will work just because they didn't implement the full spec. So it's really something painful to debug. So, but it's good. A lot of people passed. The context seems to be already bound to a device. Then why do we need to specify the device again? This is a really good question. And a context, this is a trick. A context can be bound to multiple devices. Here I show you because on NVIDIA it is not the case, but on Intel, for example, it is the case. I don't know what HipCL does, but a context can be bound to multiple devices. And in particular, if you have sub-devices. So this is why when you create a queue, you need to be able to specify which device on this context. In this case, like you say, it seems a little stupid, but it is just an implementation detail that NVIDIA backend with Intel compiler for now doesn't support this multi-device context. But in theory, it is possible. And this allows nice data sharing and everything if you do multiple GPU programming. So here it's maybe the two ways to solve the issues. You can choose which one you prefer. The first one is what we call I call the implicit. It's just you don't care. I would just use one queue, or like I give up about parallelism or about any trying to use a multiple command streamer or something like that. I trust the runtime. I will use one queue, and if you use one queue, you have no problem. The drawback is that you are using one queue. Like Christians say, GPU are really big. It's really hard to extract all the concurrency of a GPUs, right? It's super easy to port your code, but to extract concurrency is hard. One way, if you don't have a lot of concurrency, is to create multiple queues and to submit kernel on multiple queues, so they will be able to execute concurrently. This rely less on the smartness of the runtime. In theory, if you, because as I said before, queue by default are out of order. So in theory, if you execute two queues on two kernel on the same queues and each kernel doesn't occupy the full hardware, they can be executed at the same time. But you put a lot of trust in the runtime and a lot of non-determinicity because it will depend on the scheduler and everything, where creating multiple queue in some hardware will be able to, each queue, for example, will have access to one piece of the hardware. I keep this thing really general because it depends really on this kind of hardware you use, implementation you use. So you should, if you do this kind of optimization, you should really know what you are doing. But it is a possibility to use multiple queues. And as everything in HPC, everything is really subtle when you go in detail, but it is a possibility to use only one queue everywhere. And the other is to use two queues, like I said. So to use two queues, the only trick is just when you create your queues, you create a new, you use the same context. Okay, this is the only trick. And if you do that, you have no problem. You still can do Q&A-B and it will work. In fact, those examples are in the GitHub in the ATPESC 2021, inside the example, and it compile and run on NVIDIA. So both of the things are working. Does everything make sense? Do anybody have any other question? This is really maybe the more context, because if you look at a lot of tutorial, people do just queue, and after they have this kind of some issue, and I think it's better if you start in your mindset that you understand context. If you understand, you will not make this mistake. You will create implicit queue, and if you want to don't want to share any memory between contexts, you can just create queues without sharing the same context. But it is something you should be aware of. Because I spent too many hours debugging this kind of problem and I don't want to do it again. So I think teaching people will save me a lot of time in the future. So as an implementation detail for some people here who develop application, some people create a singleton for the queue. Some people create a singleton for the context or something like that. So it is a common pattern that seems people to use. If you remember before, I was talking about DPCT, the CUDA tool translator, and Abhishek can correct me if I'm wrong, but I think they do that. They have a singleton for the queue, so you can just you have a function with give me queue, and it will always give you the same queue. So it simplifies the porting if you want to do that. So just to summarize, this is a big first overview of SYCL. So I didn't go, you see, no lambdas, nothing for now. It's just platform, device, context, queue. That's it. Queue out of order. Contexts are here for memory isolation, and device are just a device. So that you can split into sub-device or something like that, but they are just device. And this is what I call unified shared memory. It's because it's explicit and you have also this malloc shared. And this work for all the backend and everything. How they implement this kind of shared is really as implementation detailed as they want. Okay, so now we know how to allocate memory. We are good. We just need to understand how to execute kernel, and this one for the people who follow the Cocos talk this morning is really similar. So they really took the same approach that as Cocos because it was a good one. Is you just need to define your kernel as a functor. So in C++, you have two big ways of declaring a functor. So I will have some example where you can just create a class and you overload the parenthesis operator, and this is a functor. Or you can just create a lambda and you pass the lambda inside your kernel. And both work as you prefer, and you have all this thing where Christian explained far better than me about if you need to capture by reference, by values, the trick with vector and all of this trivially copyable thingy and everything. So here nothing changes, regular C++ knowledge. So here the first kernel we execute on the GPUs. So maybe as a difference of Cocos, because I show Cocos here in Cocos you have this execution policies that you pass in your parallel for. It doesn't work like this in SYCL, as you see. In SYCL, you just create, you ask for devices, and you take these devices and you create a queue. So if you execute, if your device has a CPU, it will execute on the CPU. If your device has a GPU, it will execute on the GPU, right? All the things are here. So if you want to change back, if you want to run on the CPU, on the GPU, the only thing you need to do is to change your queue or context creation and to pass a different kind of device. So nothing else change. So here I would just initialize an array on the GPUs. So you have a special, if you are fancy, if you read the SYCL specification, you have some special function to initialize on the GPUs. Meminit, I think is called, or std q.fill, or I don't remember, or memset. I never remember all those names, but you can check. But here I will just do it with a parallel for. So as we showed before, I create a pointer, malloc shared, so accessible in both the CPU and the GPUs. I should say access it both on the host and the device that you choose. And then I use this queue to do a parallel for. I say the dimension, the range. So here I just want to execute from n dimension, so 0 to 129, 1729. It is the Ramadan number, the taxicab number, whatever. And after here, I pass my lambdas. And it is something who really hurt people who are porting their code to CUDA. In CUDA, like in OpenCL, you have those magic functions like get local ID or get global ID or get thread ID, who are just magic function who doesn't text anything, right? They are free function. In SYCL, it's not like this. So in SYCL, you have these introspection capabilities, but they are passed as an argument of your lambdas or as the argument of your function. So you need to pass this ID here to be able to use them. So this ID, after I will show in the example later of during this session, but you have some introspection capabilities. You can know in which teams you are, in which group you are, and everything. And in this simple example, you can just think an ID is just something where it can be cast to an integer will go from 0 to n. And this is what I do here. I use this ID from 0 to n. And after, you really need to synchronize. If you forget to synchronize and you continue, you don't know what you will access, right? It will be garbage. And those things are super hard to debug. So it's maybe better at the first step to put weight everywhere and after to remove them. And after here, I just do use a regular STD trick of, I accumulate the vector. I just do a sum of the vector just to check the result. And the result should be just n-1/2. So here in this data, I am accessing the pointer who is on the device. The device can also be a CPU, it doesn't matter, but in this case, it is a GPUs. And after I do an allocate. So you see it's pretty tidy, pretty neat, not too much, maybe if you didn't do C++ for a long time, those lambda are really strange, but after the Cocos talk, I'm pretty sure it's a candy in your mouth. It's super sweet. Any question?
Thomas,
Yes.
Can you talk about the wait feature and how that maps to the CUDA stream synchronize?
Yes, I can try to do that. So I'm not a CUDA expert, but so how it worked is it's a big analogy between a queue and a stream. Okay, I think it's correct to say that. It is out of order, so if you don't put the weight here, when you go in the accumulate, you don't know if this kernel is finished or not, right? It may be still executing. So you need to be sure when you access the data on another kernel on the CPU that you need to wait for the kernel to finish. On CUDA, I think you do a Q stream synchronize. It will correspond to Q.wait. We'll show an example that you can wait for all stream. You say, I want a synchronization point after this Q.wait. All the kernel before this point were finished. Here, I use a trick that if you are aware on OpenCL, and I think CUDA does that event, right? Too? Does CUDA have event?
Yes.
Abby?
Yeah.
Yes. So exactly here, the queue return an event, and I am waiting for this event to finish. So here it's maybe a low-grain synchronization. What is the type of that lambda that got passed to the queue? Can you pass a std function void? Okay, so I think I have some example if you want to show that. I have an example in the GitHub in 9c of hell advance. And I think after I use something with placeholder and everything, so you can place that. But maybe it's more a question for Nevin. What is the type of lambdas? And I think it is something like this indeed.
Every lambda has its own type, distinct from all other types in the system.
Okay, but in theory, I can pass a functor who took as an argument.
Yeah,
of
you can make your own function object with its own operator, open close paren, and that works. So you can just pass that as well.
Exactly.
Standard function's more problematic because it may internally do memory allocation. So
okay.
passing it, it's going to do like a normal, just host side new, and that's not going to work.
Parallel for take a templated functor. I can show you some example, but Nevin, it is a templated functor. I guess so, because like you say, all the lambda have a different type.
Yes.
Okay, my
The
101.
function object itself is not templated. In this case, it's not templated. If you used auto instead of SYCL item 1, it would be the function call operator. But
Oh,
the
yeah.
lambda, yeah, the lambda itself is just it has its own type that you can't spell it using decal type, for instance. There's no canonical way to spell it.
Thank you.
So
This is why
if you did line 9 and then line 10 and the exact same line, those two different lambdas, those would be two different types.
Exactly. Yeah, each lambdas have a unique type. So this is why it's nice to have people from the C++ community to committee to be able to do that. So maybe the question about the workgroup size, yeah, it's a really good question, and it's even the next slide. Oh yeah, exactly. So I can explain it to you now for the workgroup size, and after during the example and the hands-on, we can go more deep on this detail. So here I show you just a parallel for where you put a range, and because you are good OpenMP programmer or just GPU programmer in general, you know that GPU, like Christian say, are far more tricky than that. You need to play with the workgroup size. You need to get the workgroup size. You need to play with all of those data. Fortunately for us, SYCL just are based on OpenCL, and OpenCL are the one who invented that, I don't know, 20 years ago. So we can reuse all the same nomenclature of OpenCL. So this domain is a little painful because every different programming model called different thing, called the same thing in the different term. So sorry, I'm an OpenCL guy, so I will use the OpenCL nomenclature. Sorry if it is not match the CUDA one or the Cocos one. I put little picture, so I hope it will help. So a kernel is submitted to a queue. So a kernel is a functor with its own type and everything. And maybe the important thing is like the kernel will be invoked for each work item. Okay, so you put your kernel is like MPI. When you do MPI run, each function, each program will be executed. So here it's the same thing. Each kernel is invoked for each work item. The local work size number of work item will be grouped into a work group, and after different work group will be executed. One can think about a work group with a team. They follow more or less the same semantic. As usual, if you go deep in the detail, you have some different things, but I think for us, as for approximation, you can think about a work group as a teams. And when you issue a kernel, you can play with the number of work items, and this is what called the global workgroup size. So the global workgroup size is n, and the local workgroup size, local work size is the number of here. And I think here it's a nice picture. For example, here I have a kernel who go n is equal to 24. I don't know why I have a 17 here, and go to 24. And it is split by the runtime in your case. In our case, right, I just did parallel for, so I have no control. I let the runtime, the compiler do its best. And here I have 3 examples. So the size will be 8. The local work size will be 8. And after I have function, I will show you later in the demo, we can play with that to be able to do some introspection to get this workgroup ID, this local work item ID, and the local work ID. So you can have absolute introspection everywhere. In fact, if you are on Intel hardware, you can even know where in which hardware resources they run, but these one are really more for a ninja programmer to do really horrible things, but it's still possible. Maybe as a vectorization, so I don't show here, but SYCL have also hierarchical parallelism, and you have also this concept of a subgroup. So here, between this one can say that inside this group, they are vectorized, and they will be executed in a vector size, and this is what's called a subgroup. So you have also this subgroup who correspond to SEMD. So like Christian say, this one are teams, OMP parallel team distribute are those one, and this one are the parallel 4. And I have an example here. So here it is a parallel F4 who don't take just one range, it takes an ND range, an n-dimensional range. And this ND range, you can specify the global work size and the local work size. So if you know what you are doing, this is nice because you can tune everything. If you don't know what you are doing, you may lose the performance portability because you will auto-tune the local work size for one hardware. You will run on another hardware. It will be really totally the wrong number and you will have bad performance. So yeah, with a high responsibility, high power, high responsibility, my Spider-Man quote is not super strong today, but yeah. So you need to be careful, but it is a possibility. SYCL gives you this flexibility, of course. And this one line of code, if you want to write it in OpenMP, you will do this way. So from this global work size, you will create the group work size with just one over the other. And after you will have a group ID that you will loop over your group ID. It will be your team distribute. And inside you have this parallel for SEMD because you will do both parallel for and vectorization. And here you can compute your global ID with the formula. So I think in SYCL by default, they are, do you remember Abby? By default, it is the leftmost index, right? Who is faster if you use a multidimensional array? Don't remember.
It is C++ type, so it will be the extrememost right.
Oh yeah, exactly. Yeah, you're right. So we follow just the C++ because we see here in the ND range you have 1, but you can put 2 up to 3. We are working on some proposal to be able to have more than 3, but you have this kind of ND range. We are really similar of empty span, kind of a thing. And after you run your kernel, so those two functions are really similar on what they do, or what they should do, maybe I should say. Because maybe at the language design point of view, ND range just implies semantic, right? The only thing you do if you look at the specification is like you can synchronize between work item inside a local work size. Like in OpenMP, you can synchronize inside a team and not between teams. So it is the same thing, but implementation can really map to everything, whatever they want, right? When you wrote, you're really just agreeing on following some semantic, and after the compiler and the runtime can decide to do whatever they want, if it doesn't break this semantic. So we go pretty fast. Either because I'm super clear or because it is super clear or because you are super tired. Let's see during the hands-on, because I will not be able to talk too much, too long. But let's see. So a buffer innovation. So I think it is really something I really like on SYCL. And I think you will be a little, I have my last trivia question. I think you will be divided on both that. I think some people will really like it, and some people say it's too much magic and rely too much on some smartness of the compiler. So let's see what you are thinking. So buffer are encapsulate your data. So a little like view in Cocos. And accessor describe how you will access those data. And you always need to do accessor, to use accessor to be able to access buffer. And buffer destruction we call synchronization. Okay, so this is only 3 rules, 3 simple rules, and those just 3 simple rules will really give a lot of power and a lot of flexibilities to the runtime to optimize. So here it's the first example using SYCL buffer. So here I create n and I create a vector of size n, right? I create a queue without anything. I'm lazy, I'm saying just create a queue on whatever device you want. By default, all the runtime I know of for GPU, we choose the GPUs by default. And then I create a scope. With this scope, I create a buffer, right? You see, I create a buffer A and tick A. So now I will never use the row A. I will always use this buffer, okay? And now I need to submit a kernel to my queue. And now it's a little more verbose than before because I will need to create accessor in my queue in this queue, because I will need to say in this particular kernel, how I will access this data. So I create a queue here. And now inside this queue, using the control group handler, I say I will use an accessor and I will say write only. So you say, please, I will just write in this buffer. And no init mean you don't need to initialize this buffer with some values. I will write everything. I don't care. Just give me some uninitialized memory and I will just initialize myself. So no init. And after I run the same kernel as before, SYCL ID, IDX accessory. And then I close my lambdas, my parallel 4. I close my queue submission. So I'm here, the queue is submitted. I finish my scope here. So when I go from line 15 to like 16, my buffer go out of the scope. Because it go out of the scope, it will synchronize. So I don't need to put q.wait or parallel 4 or q.wait. I don't need to do that because my buffer will cause this synchronization. It will synchronize. It will put the data who have been used on the accessor to the buffer to A, right? And after here, I can use AI directly. And I find this thing really, really beautiful because, you know, at the beginning was C, and in C, you allocate your memory and you free your memory. At some point, we realized it was too complicated to do that, right? Everybody got double free corruption or forgot to free, a lot of memory leak everywhere. They are like, okay, we'll invent C++, we'll create a constructor destructor, and it will handle that for you. And now we are in the era of GPUs, and in GPUs, we are still on the, oh, you need to control yourself when you move your data. And SYCL arrive and say, no, okay, no, trust us. Just create a buffer and accessor, describe how you will use your data, and the runtime will be able to understand how they should move the data and where to allocate. For example, in this particular case, if you profile the code using your preferred profiler, for example, I don't know, NVProf or VTune or something like that, you will see that the memory is allocating on the GPU, and you have no data transfer from the CPU to the GPU to allocate memory, to move memory, because you say no init. So he understands that he don't need to copy, right? He can infer that really easily. Same, see, let's say after, if I copy paste this example, I will show some example later, it will minimize the number of data transfer you need to do. So we never do any spurious data transfer to, for example, GPU to CPUs, because you give to the runtime and the compiler all the information it needs to be able to know how you need to do the data transfer. So maybe it's super verbose to each time you use a kernel to create accessor. Maybe it's painful, but you give so much information to the runtime, and it's really diminish any kind of manual data transfer you need to do. So I find it really, really an elegant way of doing it. So drawback is like if you are porting your code, it's maybe painful to refactor all your code to use a buffer and accessor. But if you are developing a new code, I really encourage you to use buffer and accessor, because I really think it will really ease and this kind of performance optimization of data transfer. So I think I have the next question just to see if I was able to convince you about USM. So can I, let's see here, if you can vote on this one to see if I convince you of using the USM of the buffer. And if you have any question regarding a buffer of USM, I will be interested to know. Because the command reply I got, what happened is the accessor is accessing data based on runtime data. Yes. It's just the only thing you need to know is when you create your buffer, you just need to know what you need, right? So how it's work is after you don't use a stud vector or this kind of thing, you use buffer everywhere and you just allocate buffer to the correct dimension. Then after you use buffer everywhere and the runtime will be able to figure everything because it's really not difficult, right? At compile time, they can generate or runtime depend, but some DAG, and after they just need to execute the DAG on the correct order. It is something they all the runtime knows how to do for ages, right? Because runtime people are super smart, but they are limited by the amount of information you give to them. As you know, if you did APC for long, the easiest way to go to code performance is to be able to give a lot of information to compilers. So you say, oh, no alias, you say, yeah, please trust me, no dependencies. You say all this kind of thing, and after they know how to do that. And here you can really give them everything. So it's really nice. And we'll show some example right now if you want to do that. But it's more verbose. So when you are porting the code is really it's maybe a lot of refactoring, but from new code, I really saw a lot of good performance. Okay, perfect. Thank you very much. So I'm happy. A lot of buffer for good. Thank you very much. So I think it is my conclusion. So perfect. It is 1 hour. I was thinking, yeah, 1 hour third, so we can have after a big hands-on, and we can discuss some slide and everything. Oh, I see the buffer is either completely copied or completely not copied. Yeah, it is more or less true. You can, like Crocus, you can create sub-buffer or something like that. But yes, buffer is kind of an atomic way, something like that. Debugging infrastructure, yes, you can use GDB, for example, if you want, it works. GDB, I know on Intel we have an Intel GDB who work on GPUs, or also what you can do is just to change your device to execute on the CPU. It's not perfect because you change the behavior. You can use any VTune, it's not really a debugger, but it can give you some hints on the performance. But yeah, I use GDB, at least on Intel. I'm more, because of Aurora, I'm more an Intel aware guy, but I'm pretty sure other people are using tools. So for better or worse, SYCL is C++. So it's really like, I think the goal at the end is to port a lot of this, like Cocos, to port a lot of things on the standards. So I think it's really nice, because as you know, the C++ standard is a long, huge beast that it takes forever because they need to forward compatibilities and everything. So moving in the standard takes a long time, where SYCL, they can iterate really quickly. And because SYCL is not new, how can I say, adolescent or something like that, they have a lot of energy to change. So if you have any feedbacks, anything, for example, I know we can show that later. Before, to use share local memory, it was not possible to use this kind of explicit with a malloc to be able to use share local memory. Some people did make some issue, open the issue on GitHub, on the SYCL mailing links, and now they add it on the spec. So I think the SYCL specification people are really open-minded. So I think it's really a nice task if you want to get involved in SYCLs, or to something is wrong, is really the perfect time to fix it. I know, for example, Nevin fixed this is copy trivially copyable. Yeah, I am fighting for ND range more than 3. So.
And we're going to push for things like function pointers and virtual functions. You know, it's
exactly recursive function. I think it's a limitation for now. So
and there's a lot of overlap between people working on Cocos and and SYCL and C++. I'm certainly the overlap of all three, but there's a lot of overlap. We would have all eventually like to see this kind of stuff get into the language proper, but yeah, it will take a long time, like well over a decade.
Exactly. So
because
you can make a
C++ wants to be broad coverage, so you have to make sure this covers many whatever we do covers many vendors, and that's hard.
Thomas, there's a question like which compilation phase generates the DAGs? This is with respect to the SYCL buffers, and is there a way to view them?
Oh, this is a really good question, and the answer for the first question is I don't know. I don't know. I think I'm pretty sure it's a runtime. It cannot be a compile time, because at compile time you can have a if random generator takes this left branch, right branch, and how do you know how the compiler can generate a graph, a DAG? Maybe it can do a worst case scenario DAG. I don't know. So I'm suspect is maybe a both runtime and compile time. I have no idea. Need to do some. Yeah, I tend to vote more for the runtime because you cannot. It will be more efficient. I think it's like how you create DAG in OpenCL. You do the same thing. You just enqueue kernel with event dependencies, and all the tasks, at least most of the task-based runtime I am aware of, everything is doing at runtime. They can maybe do a little thing at compile time, but it is more your runtime. The good thing is runtime from task are a super well-known computer science topic for I don't know how long. So I think now they know how to do that. The second one is yes, but not trivially. So if we go back to this picture, I did it. So for example, I did visual. If you go about this thing, the good thing about GPU programming is we all rely on the low-level API, right? Even it is CUDA, heap, OpenCL, level 0. But everybody, whoever it is, OpenCL, OpenMP, CUDA, OpenMP, sorry, SYCL, everybody, Cocos is using at the end one of those backend. So you can trace all the code to this backend using, for example, at Argonne, we develop iProf, but you have a lot of other tools. So you have the trace of all the kernel would have executed with event, and after you can reconstruct the DAG post-mortem. So yes, it is possible. Yes, I did it. Is this exist in some production ready where you can just close your eyes and you not do it and do it automatically? No, but it should be more or less trivial with big code to do, at least totally feasible. I know because I did it for OpenCL, so yes. So mixing Cocos and SYCL, I'm a little sad that you didn't ask mixing Cocos and SYCL and OpenMP, but I'm pretty sure, yes, it is possible. I don't know why. I don't know. Now the question is how can you pass object if you allocate a memory in Cocos? How can you pass it to SYCL? This one starts being a lot of craziness, but if they live in two different kind of world, it should be possible because Cocos is just library based, so it can run everywhere. And SYCL is also library based. It's just here they choose to implement with a compiler, so it should be totally possible to use them in the same code base. The interop between the two, I have absolutely no idea. I didn't try. Like I said, for the DAG question, at the end, they just use on CUDA, for example, CUDA malloc. So at the end, they just have a device pointer. So it doesn't change anything. So in theory, yes. But as you know, in theory, you can do a lot of things. In practice, it's more complicated.
Yeah, and I'm not sure what's going to happen if third-party libraries get developed at RapSYCL and you're using Cocos. I don't think we have that yet, but if that happens, we would have to figure out how to minimize that friction.
Yeah, exactly. Because same if you use so now SYCL, Cocos have a DPC++ backend. At least it is working on it, so start being complicated. And at least if you look at the SYCL specification, and this is something I really like also about SYCL. SYCL is really clear in SYCL 2020 how you can back this raw pointer, this backend pointer. So in CUDA, you have some way of getting the CUDA string. From a queue, you can say, I want to use this CUDA string. So you can interrupt super easily, not super easily, you can interrupt, it is C++, nothing it's easy, but you can interrupt SYCL and CUDA in the same code base and be able to allocate all your memory using buffer or using a SYCL malloc, and after taking your pointer and pass it to cuBLAS. I know people who did that. And I did this kind of thing for sure with Intel backend on Intel GPUs. So let me see the agenda. Oh, so perfect. It's time for the break. So, I mean, I propose you to take the break now. And during the break, if you want, if some people have some problem connecting to Theta GPU or installing stuff, yeah, the no init, sorry, it's a different compiler didn't implement at the same rate the specification, so I missed one, sorry. So I propose, if everything is okay, I propose to maybe take a 15-minute, 20-minute break, and after we can continue with the hands-on and the example, and you can play with it and ask me any other question.